All right, we're continuing with the optimization example problems. In the previous video, we worked 4 of these example problems. In this video, we're going to work 3 more. All right, a baseball team plays in a stadium that holds 55,000 spectators. With ticket prices at $10, the average attendance had been 27,000. When ticket prices were lowered to $8, the average attendance rose to 33,000. Find the demand function assuming that it is linear. And then how should ticket prices be set to maximize revenue? Okay, so this is not a business class, but when we went through this section of the textbook, the optimization problem section of the textbook, there was at the end there was a section that it talked about the idea of a price function, a demand function, a revenue function, cost function, and this was just to give us a sense of an example application. So I don't want to get too bogged down with the actual business analysis here, but right, because this is more about the calculus. It has nothing. Don't get bogged down with trying to understand the business concepts here. We're just using this as an example. Okay, so the idea was the demand function is that was the price function. They also call that the demand function. Price as a function of the number of units sold. So if you sell more units, then that means you lowered the price. If you lower the price, you can sell more. If you raise the price, you're going to sell less. That's in general how demand works. And they're saying, okay, so what's the demand function, assuming that it's linear? So if we want to make we're going to make a line for the demand function, we need either a point and a slope or 2 points that relate the units sold to the price. All right, so, well, okay, we see that at the price of $10, 27,000 tickets were sold. Okay, and so the price function or the demand function is going to be price as a function of units sold, and so the units sold is X. Price is Y. The dependent variable. Okay. Now, what else do we have? Well, it says when the ticket prices were lowered to $8, the average attendance rose to 33,000. So we have another point. Okay, so we've got 2 points, and we're assuming that this function is linear. So let's just get in the equation of a line that goes through these 2 points. So M is y2. Let's say this is point 2. This is point 2. This is point 1. So y2 minus y1 over x2 minus x1. Okay. So minus 2 divided by 33 minus 1 over 3,000. And it makes sense that the slope is negative because if you increase the number of units sold, that means you're lowering the price. As the X goes up, the price goes down. Okay, so now let's write the formula for the line. So, okay, Y minus Y1, let's pick a point here. Let's use this point. Y1 is 8 is equal to M times X minus X1. Okay, so Y is equal to minus 1 over 3,000 X plus 33,000 divided by 3,000 is 11 plus 8 or plus 11 and then add 8. So this is going to be plus 19. Okay, so there's the line. So what we're going to do is we're going to so this Y here is the price as a function of X, which is the number of tickets sold. So 19 minus 1 over 3,000 X. Okay, and then X is greater than or equal to 0. Well, no. X is greater than or equal to 0, and then less than or equal to 55,000. That's the capacity of the stadium. So there we go. There's the demand function. Okay, now how should ticket prices be set to maximize revenue? Okay, the revenue function is you just take the price times the number of tickets sold, or the number of units sold. So revenue is equal to X times the demand function. Okay, so which is, okay, so this is R of X is equal to 19X minus 1. And so with domain, same domain. So all we need to do is find the maximum value of R, of the R function over this interval here. And then once we have that'll give us an X value and an R value. Then we just plug that X value in here to get the price. Okay, so this is a closed interval, and this function is continuous. So we're still just using the closed interval method. We haven't had to use some special, so we haven't had to do anything different from the closed interval method, which is nice. But it wouldn't be a problem if this wasn't a closed interval. If this went off to infinity or something like that, that wouldn't be a problem. But okay. So the closed interval method, we evaluate the function at the endpoints. So R of 0 is 0. That makes sense. There's no revenue if you don't sell any tickets. Okay, so let's see. So we've got 19 times X minus, so X squared over, we'll store that as E. Okay, so E with X is equal to, I mean, you would think that this would be the largest revenue. You sell the most tickets, but this is not a business course. But you're just seeing the application of finding absolute maxes and mins over real life functions. So 36,667. Okay, now we want to the closed interval method. We find the value of the function at critical numbers. So there's the derivative. Now solve for when this is equal to 0 for X. X is equal to 28,500. So let's evaluate the function at 28,500. 270,750. R at 28,500 is equal to 270,750. So that's the max revenue. How is that possible if you're selling more tickets here? Because remember we sold more tickets, but we had to compromise price to sell these tickets. So it's that perfect balance of price and tickets sold is here. Okay. Now, what's the price? That's the revenue. That's, if we're going to maximize revenue, that's the revenue. But it's asking us what do we have to set the ticket prices at to do this? So what is P of 28,500? 28,500 divided by 3,000. $19 minus that. $9.50. An observer stands at a point P, 1 unit away from a track. Two runners start at the same point S in the figure and run along the track. One runner runs 3 times as fast as the other. Find the maximum value of the observer's angle of sight theta between the runners. All right, so the variable we're trying to optimize is this theta. It's not really optimize. Optimize, kind of that term to me implies like you're designing something. This isn't a design, but it's still the same type of problem because we're trying to find the absolute maximum value or minimum value of this based on the scenario. So it's the same type of problem. All right, the idea is we're trying to optimize this theta. We need to express theta as a function of a single variable. That's where we're trying to get to. But we start by, we use this diagram here and insert other variables, and we're going to get theta as a function of other variables. You have to define what theta is with any equation, and then from there try and relate the input variables to get it to a function of one variable. So let's see. We've got, so this distance, so this distance, this distance, and then, yeah, so you've got these two distances, and then you've got this distance here. Okay, so this, we'll say this is x1, this is x2, and this is x3. Okay, now we should be able to relate, all right, if we just want to get a basic equation for theta here, so, okay, well, all right, well, let's try and relate these variables, because we should be able to relate these variables, because it says they start at the same point S, and then this runner is running 3 times as fast as this runner. Okay, so at some time t, the idea is at time t is equal to 0, theta is equal to 0. And then as time increases a little bit, even the slightest amount, theta is all of a sudden greater than 0 because this runner has gone ahead of this runner. And so, and then as time increases, this theta gets bigger, and I'm assuming based on the geometry, it'll get to a point where theta maxes out. Even though this runner is still gaining, is always gaining or pulling away from this runner, eventually theta is going to max out, and that's what we're trying to find, that max value. Okay, so, but all right, at time t is equal to 0, x1, x2, and x3 are all equal to 0, but just a little bit above time t is equal to 0, you know, at 1 second, whatever, what do we have? So the idea would be that if we're at some time t, then this runner is, so let's say we've got, this is runner 2, this is runner 1. All right, so you've got the rate of 2 and the rate of 1. So at time t, distance is equal to rate times time, x3 is equal to r2t. All right, x1 is equal to r1t. Okay, and then since x1 plus x2 is equal to x3, then x2 is equal to x3 minus x1 is equal to r2t minus r1, or r2t minus r1t. So x2 is equal to r2 minus r1t. All right. But we know the relation between r1 and r2 because we know that r2 is running 3 times as fast as r1. Right? So, all right. So 3r1t is x3. This is just r1t, and then this would be, so r2 is, so 3r1 minus r1t, so 2r1t. Okay? Yeah, there we go. So x1 is r1t. All right. X1 is R1T. There's X1. What is X2? 2R1T. 2X1. You see? What is X3? 3R1T. 3X1. So there you go. There's the relation. This is 2X1. This is 3X1. There we go. Okay, great. Now we're in business. Okay, so it would be nice if this theta was like already in a right triangle, but it's not. And so we're going to need to kind of relate theta to this bigger right triangle here. So let's call this alpha. Okay. Now with that, we can say that, so opposite over adjacent. So tangent of alpha is equal to opposite, which is 3x1 over adjacent, which is 1. So 3x1. All right. Now, we can also, with this angle here, would be alpha minus theta. So tangent of alpha minus, or no, it would be, alpha minus theta is equal to x1. Okay, so now let's use the trig identity for tangent of like a minus b. Tangent of a minus b is equal to tangent a minus tangent b over 1 plus tangent a tangent b. All right, so we've got tangent alpha minus tangent theta, and then 1 plus tangent alpha tangent theta is equal to x1. All right, but we know tangent of alpha is equal to 3x1, so let's substitute that in. 3x1 minus tangent theta over 1 plus 3x1 tangent theta is equal to x1. There we go. Now let's solve for tangent theta. So cross multiplying, we get x1 plus 3x1 squared tangent theta is equal to 3x1 minus tangent theta. If we come up here, okay, so we've got tangent theta plus 3x1 squared tangent theta is equal to 3x1 minus x1 is 2x1. All right. Tangent theta 1 plus 3x1 squared is equal to 2x1. So tangent theta is equal to, and then okay, and then x1, what's the domain of x1? X1 could be 0, not less than 0, and then go to infinity. So there you go. There's, we got, well, it's more of just an equation. I don't know if this is written as a function, but just a relation between theta and a single variable. All right? And so we saw when we went to the textbook, we can use implicit differentiation to solve an optimization problem. So let's find the absolute maximum value of theta. If there's a relation here between theta and x1. I mean, actually, it would probably be better to, so theta is equal to, yeah. And then x1, there you go. Arc tangent is a function, And then with the argument here, this 2x1 over 1 plus 3x1 squared, that's also a function. So this is a function, all right? So let's find the absolute maximum value of theta over this interval here. So this is not a closed interval, so we need to use the alternate analysis techniques. And so let's just go ahead and plug this in as a function here. So 2 times x divided by 1 plus 3 times x squared all right. Okay. So what is theta when x is equal to 0? That's going to be 0 based on the diagram. But let's just check, because we want to check the endpoint behavior. 0. Okay. Now, for the other endpoint, we say, what is the limit as x approaches infinity of theta? Okay. So we take the limit as x approaches infinity. That also goes to 0. That's very interesting. So as the distance goes to infinity, so the time, you can think about this after the start time, the time goes to infinity, this theta goes back to 0. It starts at 0, goes back to 0. Interesting. Okay, so the idea is we've got some function for theta. Theta as a function of, I guess it would be time. Well, no, as a function of x1, which is also kind of a function of time. Theta starts at 0. It's going to come up and then come back down to 0. I mean, I just drew a parabola here, but yeah, that's not going to be parabolic. But that's the idea. Okay, and so the only way we need to analyze we need to find the critical points. If there's just one critical point, then since we can see this is continuous. Yeah, there's nowhere where this is continuous everywhere. There's nowhere where the denominator can divide by 0. Arctangent is continuous everywhere. So if there's only one critical point, then that critical point has to be the absolute max. And I talked about this idea in the preview of optimization problems video. Okay, well, let's see how many critical points there are. So take the derivative. Okay, solve for when equal to 0. Okay, so x is equal to minus 3 root 3 or 3 root 3. This is outside of the domain. So x is equal to, this is 0, root 3 over 3, x1. Okay, now we're not done though, because we have to make sure that algebra solve, is there any x that makes the denominator 0? No. Okay, so that's the only critical number. All right. So that's the absolute max. Well, assuming that this function, it starts at 0 and ends at 0 over the domain, assuming that between those points it goes up, if we put in any point between 0 and infinity and it's positive, then that's going to be the absolute max. Because since it's continuous everywhere, it couldn't. All right, so we have a critical point where the first derivative is equal to 0. That's the critical point, right? The first derivative equals 0. That's the only way it can get back to 0. It has to turn around and come back. With a continuous function, there's no other way. Like it couldn't start at 0 and get back to 0 and also have a value that's greater than the value at this critical point. If this is x1 is equal to root 3 over 3, it starts at 0 and ends at 0 as x goes to infinity. So this is more of a, it's not like this. It's more of a, It doesn't end at 0 like that. It does this. It's more of like, it's a horizontal asymptote. Okay? It can't, there's no way for the function to ever be bigger than this value and not have other critical points. So just go take a look at, go watch the preview of optimization problems video and you'll see what I mean. Okay, so we've got the function with x is equal to, and we'll put root 3 over 3. Pi over 6. So theta at root 3 over 3, theta evaluated at root 3 over 3 is equal to pi over 6. So that's it. Theta is equal to pi over 6. That's the maximum value. Okay. So x1 is going to be root 3 over 3. That's going to be the distance in whatever these units are. Whatever this is 1 unit, whatever that is. It'll be root 3 over 3, and theta will be pi over 6 radians. All right, the blood vascular system consists of blood vessels, arteries, capillaries, veins, that convey blood from the heart to the organs and back to the heart. This system should work so as to minimize the energy expended by the heart in pumping the blood. In particular, this energy is reduced when the resistance of the blood is lowered. One of Pascal's laws gives the resistance R of the blood as, R is equal to CL over R to the fourth, where L is the length of the blood vessel, R is the radius, and C is a positive constant determined by the viscosity of the blood. Pasquale established this law experimentally, but it also follows from equation 8.4.2. The figure shows a main blood vessel with radius R1 branching at an angle theta into a smaller blood vessel with radius R2. Use Pasquale's law to show that the total resistance of the blood along the path ABC is... so let's find the total resistance of the blood along the path ABC. So we're gonna do R from A to B, and then add that to R from B to C. All right, this is not a biology video here. We're just, don't get bogged down with the biology here. I'm just going to keep it simple. So R from A to B is this constant C, LAB over R1 to the fourth. But we want to express this in terms of all the constants given here. So, what is this distance here? What is this distance? This distance is LB. So this LBC, so tangent of theta is equal to opposite over adjacent, B over that distance. This is X. Let's say this is like X. So X is B over tangent theta, you see? So this is going to be B over tangent theta. All right? And so with that, LAB is A minus B over tangent theta over R1 to the fourth. There we go. That's RAB. Okay, now RBC is going to be equal to this constant, and then LBC over R2 to the fourth. Okay, now what is LBC? That is, so sine of theta is opposite over hypotenuse. So sine of theta is opposite over hypotenuse. So B over sine theta is LBC, right? LBC is B over sine theta. Okay, so C and then B over sine theta over R2 to the fourth. All right. So then the resistance, the total resistance along the path ABC is this RAB plus RBC. So C, you can factor out the C. And then, so it would be A minus B tangent theta over R1 to the fourth plus B over sine theta R2 to the fourth. Let's look here. So we can write it as cotangent theta, and then 1 over sine theta is cosecant. So we'll do it, we'll say, so A minus B cotangent theta over R1 to the fourth, right? That's cotangent. And then plus 1 over sine theta is cosecant, B cosecant theta over R2 to the fourth. And there you go. Okay, prove that this resistance is minimized when cosine theta is R to the fourth over R1 to the fourth. Okay, so looking at this, the idea is we're going to want to differentiate R with respect to theta. That's how we're going to be able to find critical points to get the smallest resistance. So here, this function here, the domain is, so I guess theta would be less than or equal to pi over 2, less than or equal to 0. I mean, I don't know. I'm not a doctor or anything, but I don't imagine they're thinking about this going less than 0 or greater than pi over 2. And so the idea would be you would plug in theta is equal to 0, theta is equal to pi over 2, and then look for critical points and see if there's and find which value the endpoints or the theta that's in between 0 and pi over 2 minimizes R. Okay, but so we'll need to take dr d theta, but when we look here, so R1 and R2 are not dependent on theta. Okay, A is not dependent on theta, but B is dependent on theta, right? B is a function of theta. A, no. R1 and R2, no, but B is. So if we're going to differentiate R with respect to theta, we can't treat B as a constant. And I'm looking at the solutions manual, and they treat B as a constant. Not the solutions manual for the James Stewart, the author, but I'm looking on Chegg. And what they do is they get dr d theta, and they treat C, R1, R2, A, and B as a constant. But to me, you can't do that. And then they set dr d theta equal to 0, and from there, when you do that, you can solve and get this. Or no, it's... Okay, and the idea is based on the nature of the function. If you can just show that there's no way that the endpoints are going to be the absolute minimum value, and then this would have to be the absolute minimum value associated with dr d theta equaling 0, like associated with a critical point. But to me, you can't do that because you can't treat B as a constant. You have to know how B depends on theta. So I don't know. That's why I don't like these real world example problems, because it's just getting all mixed in with, we're not students in biology, So I guess perhaps James Stewart intended you to treat B as a constant, but it's not with respect to theta. Okay, and then find the optimal branching angle correct to the nearest degree when the radius of the smaller blood vessel is 2/3 the radius of the larger vessel. Okay, well, all you would do there is, they're saying that R2 is 2/3 R1, so you could just plug that in here, and you're going to get cosine theta is equal to some number. Take the inverse cosine, that's the value. Why is that the theta? Because, let's do that. So, okay. R2 2/3 R1 to the 4th over R1 to the 4th. So 2/3 to the 4th. And then the R1 to the 4ths cancel, so 0.198. So the theta is equal to the inverse cosine 0.198. .37 radians. Okay, and that's going to be the optimal because this is the value that minimizes R. That's the idea. And also in the solutions, they talk about how you would, so to analyze why this is the absolute min, that they use the second derivative test to show that this is a local min. And so, yeah, you'd have to go through it carefully and analyze it to make sure that the endpoints aren't, I mean, yeah, all you have to do is show for the closed interval method, if you show that the endpoints are, you evaluate the function at the endpoints, and then you evaluate the function at if there's a single critical point, as long as you show that the value at that critical point is lower than the endpoint values, then that has to be the absolute min if there's no other critical point. So, but then you could also do like a second derivative test to show that it's a local min. You could use all the techniques that we learned in chapter 4 to prove to yourself that you have the absolute max or min if you're doing an optimization problem.